when we think about these indefinite or these definite integrals being net areas, we would now like to think about symmetry. How can we possibly use symmetry, right? We can use areas of shapes to help us find net areas, but how can symmetry be used? So just a reminder, when I'm talking about symmetry, I'm talking about even and odd functions. So we said an odd function says f of negative x equals negative f of x for all x. And that was an odd function. An even function is f of negative x equals f of x for all x. So graphically, we also had a nice visual of what's taking place with these odd and even functions. So with an odd function, that could be something like x cubed, for instance. The type of symmetry that we saw here had to do with this rotational symmetry. So the symmetry is rotational by 180 degrees around the origin. So that is one way to visualize odd, is that we have this. Now, another odd function that we've seen a lot was sin x. So sin x, for instance, look like the following. We had rotational symmetry, and we also had the fact that sine of negative x was negative sine of x. So this is sine. So we have this, again, this rotational symmetry taking place here. For an even function, so this would be sine. For an even function, we have the symmetry was reflected over the y-axis. So our symmetry, this is reflection over the x or the y-axis. So this is something like x squared, for instance, was a perfect example of an even function. We also had something like cosine, right? So the graph of cosine of x was also an even function. So sine and cosine are really nice examples that aren't just trivial powers of x that are even and odd. So if we think now about integrals, how does that relate? So if I took the integral from, say, negative a to a, if I have an odd function, so if I went from, say, over here from negative a to a, if we think about net areas, remember we said area above the x-axis was positive, area below the x-axis was negative. So if I think about the net area for an odd function, and here it would be looking at this versus this area. Well, which one's going to be bigger? Well, if this is odd symmetry, if I rotate this, these should be identical to each other. So if you have the same positive and the same negative area, the net area, as long as we go from negative a to a, so remember this has to be the same distance, this is going to be 0. If we went from, say, negative 1 to 4, then that's not going to be 0, right? It has to go the same distance in both the left and the right direction. For an even function, if I was to, say, go from negative a to a over here, or again, go from, say, negative a to a, if we look again at what is going to be similar between these two sides of this, well, we see it's just the same, right? This area is the same as this area. This area is the same as this. If I was to put this below the x-axis, those two areas would be the same. So the trick that we have here for an even function is this is going to be just double the integral from 0 to a of f of x dx. So we have these symmetries that we can use for us. Just viewing these as net areas, either the positive and the negative will cancel each other out and you're left with 0, or if it is an even function, you can just simply work with half of it and then double that. This is going to be really nice for some specific examples where trying to use the fundamental theorem of calculus by taking the antiderivative will be pretty much impossible. But if you notice that it's the same number on the bottom as it is the top, you could simplify this. So an example of what I'm referring to would be the integral for, say, negative 4 to 4 of sine of x cosine squared of, say, 5x plus tangent of x times secant of x dx. You have no way of being able to figure out what this would be using any type of antiderivatives. This is a really nasty one. But instead, what we could figure out is this odd or is this even? So if we look at this, if we look at my function, f of x is sine of x, cosine squared of 5x, plus tangent of x, secant of x, I plug in negative x. So I have sine of negative x, cosine squared of negative 5x, plus tangent of negative x, secant of negative x. If we remember things about odd and even functions for all of our trig values, this sine is odd, I pull out the negative. Cosine is even, the negative becomes a positive. Tangent is odd, I pull out the negative. Secant is even, that becomes something positive, that gets rid of the negative. So this becomes negative sine of x, cosine of 5x, minus tangent of x, secant of x, which is just the same thing as negative f of x. So what this says is that this is an odd function. If it's an odd function and the bounds go from negative the number to the positive version of that number, this whole expression here is simply equal to 0. So you could simplify that by not having to do any type of antiderivative, but knowing things about this symmetry allows things to simplify quite nicely.